So I'm going to talk about distributionally robust deep learning-based image reconstruction. So this is work with a number of my colleagues. So Mohammad so I'm going to talk about 4 related papers. And the first paper is a work by Tobit Klug. The second one is by Mohammad. And the third one is a collaboration between Daniel, Chiayo, and me. And Akshay is a collaborator who has been helping us with making sure that all the MRI experiments make sense. All right, so we consider the accelerated MRI problem. So the accelerated MRI problem is as follows. We have some image, and it's undersampled, in this case, by a factor of 4. And what you see here, those lines, those are the frequencies or the information that we actually see, and the black lines, that's information that we do not see. And so from this undersampled information, our goal is to estimate the original image. So as you have already seen from the tutorial and from Marty's talk, we know that deep neural networks trained end-to-end give excellent performance. So neural networks trained to map effectively the undersampled measurement to a clean image outperform classical methods by a significant margin. And there are a number of ways how you can do this. So, first people have been using convolutional neural networks, and then this has evolved to people using transformers, like in Marty's work, for example. And again, this performs really well, both in terms of computational speed. So it's super fast because all you need to do is like a forward pass through your network, and it gives you really good imaging performance. So now there are like 2 components to this, right, to this performance. So the one component is the models and algorithms that are used, for example, whether you're going to use a convolutional network, an unrolled network, things like that. And then, of course, it matters very much which data you train on. So now if we look at some related problems in machine learning, so for example, in natural language processing, then we have seen that scaling up the dataset size and scaling up the models gave significant improvements in performance. So here, what you see is, let's just look at this middle plot. You see a transformer that has been trained on varying dataset sizes. And as you can see, the larger you make your dataset size, and if at the same time you also scale your model, then you really get this performance improvement, right, that follows the scaling law behavior. And this has been pretty accurate, and from this we kind of know that if we, for example, multiply our data by a factor of 10, then we get a certain kind of performance improvement. And the same has been true for image classification models, for models in vision. So what you see here is the image net error rate, and you see again the performance as a function of the dataset size. And again, what happens is if you increase the dataset size, and at the same time you increase the size of your model, then you get a performance increase that follows this scaling law. And so this has been, this kind of observation has been driving a lot of the improvements lately, right? Because people have been just collecting more data and making models larger. So now if we look at image reconstruction problems, then we see that the dataset size is actually really small. So for example, there is this paper from 2015 where they trained CNNs to perform denoising. It works super well. They only trained on 90 images. Then there has been another paper where they did compressive sensing, for example, on the fast MRI challenge. This data set is only 35,000 images large, right? And many of these images are actually quite related because they were obtained by like volumes, and the neighboring images are actually really similar. So now if we look at what has been happening recently, the very best performing model for denoising as of today is the Swin transformer. And the Swin transformer has also been trained only on 10,000 images, right? So the dataset sizes for imaging problems are relatively small compared to what we have been seeing in natural language processing and so on, and for prediction tasks. So for prediction tasks, we have seen that, the state-of-the-art models for image classification and natural language processing, they have been trained on like billions of examples, right? So now the question is, can scale improve image reconstruction performance, right? Like with scale, I mean, what if we just take existing models, make them larger, and at the same time also scale the number of images that we train on? Does this significantly improve performance? So is this like a way forward? So let's see what we would expect just by looking at like a very, toy model. So let's say we have a signal X, and the signal X is, like, imagine it's relatively high dimensional, so it's an image. Just for the sake of, this toy example, let's assume it's drawn from a d-dimensional subspace. And the d-dimensional subspace is supposed to model, some low-dimensional image manifold. So let's look at a denoising problem. So let's look at a measurement where x or where y is equal to x plus some noise, and let's just consider Gaussian denoising. So for this Gaussian denoising problem, a linear estimator is actually optimal, but what we do is we consider a linear estimator that is trained on n many examples through empirical risk minimization. So that's kind of a toy model for a neural network. So now this is our risk. W times y, that is the estimate of our signal, and x is the original image. So what we assume here is we are drawing data from this, like pairs of measurement and a signal. And then we are doing empirical risk minimization, and we look, well, how does the error behave as a function of the training samples? And it can be shown relatively easily that the optimal early stopped estimator obeys the following bound. So the mean square error is smaller or equal to the mean square error corresponding to the optimal estimator plus some term that is, some quantity depending on the dimension of the signal divided by the number of training samples. So from this we can see that from this we can kind of see the expected performance behavior for this toy model. So the expected performance behavior is as follows. If we have very little training data, then we're kind of in a regime where nothing good happens, right? So we expect like a relatively high error. After this, there's this power law region, and in the power law region, the error behaves roughly as n to the power of minus alpha, where alpha is something around 1. But then at some point, the error that corresponds to learning the signal model becomes so small relative to the irreducible error that we reach this irreducible error region. And the irreducible error region would be the error that the optimal estimator achieves for our toy model, right? So this holds precisely for our toy model, but that's really the behavior that we expect in general, right? So we really expect that there's going to be some power law region. In this power law region, increasing the amount of data should help. But then at some point, we come to some irreducible error region. And in this region, increasing the amount of training data should not help to improve our models. So then the question is, well, for image reconstruction methods, in which region do we lie on? It's really an empirical question. Or at least I don't see a way to answer that theoretically. So we looked at this empirically. So we first look at the UNet. It's like a famous convolutional neural network, and it gives almost state-of-the-art performance for a number of imaging problems. So what you see here is the following. So let's just look at this point first. So this point means the model is trained on roughly 500 images. And so what we did is we trained like a number of models, and we increased the size of those models. So what you see is, like for this particular size, look, let's say 500, there is one curve. So here we train a model of a particular size on data set of size 500. You make the model larger, train it also on 500, make it even larger, and so on. So you see for every point, there's an optimal model size, right? So as you increase the data, you also have to increase the model size to get optimal performance. And so this plot shows the performance of like the, let's say, optimal model size or empirically optimal model size, right? And so what we see here is, as we make the training set size larger, this power law behavior already slows at very small number of training set sizes. So for example, if we have 10,000 images, then the scaling behavior that we get at that point is already so, so little that even if we were to train on like 1 million examples, the performance improvement would be, or the expected performance improvement, I mean, we don't know for sure, would be extremely small, right? Okay, so this holds for unit-based denoising. So let's look at another problem. So for example, let's look at, let's actually look at a transformer model next. So as René, for example, mentioned, what we have seen in other problem is that if we scale the data and if we scale the models, then transformers perform actually particularly well. So for example, if we take a CNN, we just make it larger, train it on more data for prediction tasks, we also sometimes hit like an error floor. But what we have seen is when we scale transformers, they typically show like a better improvement as we increase size and training set size. So then the question is, well, like for image reconstruction, the same could be true. But now as you see here, the transformer-based model has, exactly the same behavior as the unit-based model as a function of the image set size. It just performs better overall. It's just like a better model. But the expected performance improvement for, in this case, like the best transformer-based model is also not higher, than what we see with the CNN. And this model here, that is trained on 10 to the power of 5 examples, that model really gives state-of-the-art performance for like a number of data sets in denoising. So this is really like the best you can achieve so far. And this shows that if you go from the current state-of-the-art, if you improve, right, if you increase the data set size, you do increase the performance, but it's just by such a tiny bit that you just can't see it, right? Okay, so the conclusion from this experiment or from the study is that we see only very marginal in-distribution performance gains, or we expect only very marginal in-distribution performance gains as we scale the amount of data. What we also have seen kind of, from the development in the past 2 years is that there are also very marginal in-distribution gains from model improvements on things like fast MRI. So 2-3 years ago, people came up with these unrolled neural networks, right? And they perform extremely well. So now there are some things that have been improved. For example, as Marty talked about, if you incorporate transformers in such unrolled networks, you do get like a small performance improvement, right? But it's just, if you look at the fast MI data set in the past few years, what has been achieved by playing around with different models has been just like a very minimal improvement, right? So from this, I would kind of conclude that we have very marginal in-distribution gains by scaling data, very marginal gains from model improvements, right? So then the question is, well, like, is this like the best we can do? So now, this statement really pertains to what I would call like, or what everyone calls like in-distribution performance. So in-distribution performance means we consider the following setup. We have a data source. So for example, we have MRI scans from a particular hospital, from a particular scanner and so on, right? And then we take this data source and we generate a training set and a test set from this data source. But the important point is it's really the same data source, right? And then we train a model on the training set and test on the test set. So that's how all these models are evaluated. Now, this does not really reflect performance in practice. And what I mean with that is, in practice, you have a number of robustness concerns. So there are kind of 3 robustness concerns that come to mind. So the first one is adversarial robustness. We already talked about this yesterday in the tutorial, right? Adversarial robustness in image reconstruction means if we have a network and we reconstruct based on an uncorrupted measurement, we get like a nice image. If we perturb that measurement, then we get suddenly like a measurement, like a reconstruction that doesn't look as nice. So now in image reconstruction, you don't really have an adversary in your MRI scanner, right? So the concern is not that you have like an adversary messing with your data, but the concern is that you have, for example, a patient moving, or that you have like a coil failing in MRI. So there are kind of worst case perturbations in MRI and imaging modalities. So we looked into these adversarial perturbations like ourselves, and we looked at the literature, and I think what one can conclude is that they are not as much of a problem in image reconstruction as they are in classification, in the sense that like every method is somewhat sensitive to adversarial perturbation, and neural networks are not particularly sensitive relative to things like L1 minimization. Then there's a second concern, and that is related to reconstructing fine details. So here's an example that illustrates this, which is from the FastMI competition. So what you see here is, you see the reconstruction of an image from, from a knee. And what you see here is a pathology. This pathology is only a few pixels large. So in the competition, there was not a single network that could reconstruct this pathology. And here it looks like there is no pathology. And so the concern is that neural networks cannot reconstruct such fine details. So now if you look into this in detail, then it turns out that no method gets this pathology right, because of course if your pathology is so small and you're undersampling too much, then you just don't have this information about the pathology in your data. Now if you compare different methods, you actually realize that your best bet at reconstructing this pathology is actually the neural network. So if you look at a lot of pathologies and look how well are they reconstructed, then we found that the neural networks that give overall best performance also do best in reconstructing fine details. So it is a concern, but it's just, if you undersample too much, of course you can't reconstruct these fine details, right? So it's just like a general concern. And then there's this concern of distribution shifts. So let's say you train a network on knees and then you apply it to brains, then you get like really poor performance. So turns out, you know whether you train it on brains or on knees, so that's not, a good example of a distribution shift, but there are other distribution shifts in practice that occur. And based on what we found, the distribution shifts, that's really the issue in image reconstruction. So training on a certain distribution and applying it to another distribution, that's really where we lose a lot of performance. So that's what I want to talk about for the rest of this talk. And the story is going to be that what we saw now is that there's very marginal in-distribution gains that are expected from scaling data. There are marginal in-distribution gains from model improvements, right? But it turns out that actually increasing the training set size by including more diverse data and by developing better algorithms, we can actually improve the performance in practice significantly. And what I mean with improving performance in practice is really making models that are distributionally robust, that are robust under distribution shifts. And it turns out this is very feasible for image reconstruction problems. All right, but let's first start with an experiment to see what the issue is when we have a distribution shift. So let's look at a dataset shift. So that's actually really a realistic distribution shift. So here the setup is as follows. We have the FastMI data, comes from a university, NYU, it's collected with a particular kind of scanners and so on. And here we have a data set from Stanford. It also consists of knees, right? But there are some differences. It's collected with a scanner that has slightly different settings, has a slightly weaker magnet, things like that. So there are small differences, but they turn out to matter. So now what we're going to do is we train methods on the training set, and then we evaluate them on the FastMI test set, so that would be in distribution evaluation, and we also evaluate them on the Stanford test set, that would be out of distribution evaluation. And we're going to look at different reconstruction methods to illustrate a point. So we're going to look at classical reconstruction. So now if you go to a hospital today, if it's not like the most modern one, most likely L1 minimization is going to be used for reconstructing, right? So L1 minimization is technically a method that is not trained based on data, right? But if you look closer, it is actually tuned based on data, because you have one regularization parameter, and that regularization parameter is chosen based on data. So it's also data dependent, right? That's the point I want to make. So yesterday we also talked about neural networks that are untrained, so the deep image buyer, for example, they are also not trained based on data, but they also do have hyperparameter. In this case, let's say 5 hyperparameters, just to be concrete. And those hyperparameters are also chosen based on data. Now, if we look at an end-to-end neural network, like a UNet, a variational network, or like a Hammers net, then it's, you know, it has like, let's say 50 million parameters in our case, because that's what fits in our GPUs, right? And what I want to look at now is, well, how do these different methods, like what would we expect, how do they perform relatively to each other on the FastMI data and on the Stanford data? So what you're going to look at is as follows. So let's just think this through. Like, let's say we have L1 minimization. So L1 minimization doesn't perform as well as neural networks, right? That's what we know based on the challenges. So on the FastMI data, maybe it's going to get performance like, let's say, 0.7, something like that. But it only has one hyperparameter, right? So we only have one hyperparameter that is, you know, tuned based on the data, so we expect it to not be so sensitive to a distribution shift. So maybe we would expect that we get a very similar performance on in-distribution data and on out-of-distribution data. And if we get a very similar performance on in-distribution data and out-of-distribution data, we would expect L1 minimization to lie on this line, right? So now if we think about these untrained neural networks, they perform a little bit better, so we would expect them to lie higher on this line. So the neural networks, now that have 50 million parameters, they perform really well on in-distribution data, but at least I expected them to be more sensitive to distribution shift, which means that they would lie somewhere here maybe, right? Meaning that they perform really well on in-distribution data, but not so well on out-of-distribution data. So I was expecting something like this to happen in terms of performance comparison, just roughly. Another thing that could actually happen is that all methods perform a little bit worse, because it could also be that the Stanford knees are just harder to reconstruct than the New York University knees. So for example, if you have an MRI scanner that has like a bigger magnet, right, you have a higher signal to noise ratio, and therefore you would expect better performance on such a data set, right? So it could also be that all the methods shift, but then we would have expected that the variational network and the UNet, they shift more just because they have more parameters, right? So they should be more sensitive to a distribution shift. So now what actually happens is the following. So what we see here is just different methods. So L1 minimization, there are different ways how you can do L1 minimization. You can do total variation minimization, you know, you can do wavelet, you can use wavelets as a regularizer and so on. Same for UNets. There are different choices of UNets, there are different choices of untrained networks, and there are different choices of variational networks. So now what we see here is that all the methods perform significantly worse under the distribution shift, but the ranking of the algorithms is actually preserved, right? Meaning that the network that performs best on in-distribution data, in this case, the variational network, also performs best on out-of-distribution data. And this holds true really broadly. So here we looked at a dataset shift. Of course, there are other kind of distribution shifts. For example, there's an adversarially filtered shift, same story. Then there is an anatomy shift, meaning that we train on brains and reconstruct based on knees. We see something very similar, right? So maybe you have seen these sort of plots before, because there is a very nice line of work by Ludwig Schmidt and collaborators, and they found these very similar risk relationships for prediction problems. So prediction problems are things like, you know, classification, regression, and so on, right? And what you see here, and that's again from a paper from Ludwig Schmidt and his collaborators, what you see here is each point corresponds to a particular model, right? And then here you see, for example, the performance of, like, so the model is trained on ImageNet. So here you have ImageNet performance, and here you have ImageNet v2 performance. So this would be in distribution, out of distribution evaluation, right? So we see these sort of linear risk relationships for prediction problems. So one thing that we were really curious about was, well, like if we see these sort of linear risk relationships in prediction problems and in reconstruction problems, then maybe it's something universal that could be potentially interesting to study. So now if we look at the theory for performance under distribution shifts, then here's the kind of theory that you find in a textbook or in classical papers. So let's say you have a distribution P and a distribution Q. Then there are a number of theoretical results. So here's an example that relate the performance on the two distributions for one model by bounding the difference in performance as some function of the distance between the distributions, right? So for example, if those distributions are really close together, then you would expect your functions to, lie the relationship between those two risk bounds to be somewhat in this band here, right? But what we would like to do is to have theory that relates the in-distribution performance and the out-of-distribution performance more precisely as a function, like as a curve like this, essentially. So what is kind of desired is to understand for what sort of setups, so meaning distribution shifts and estimators, do we have a relationship like this, that the out-of-distribution risk is a monotone function of the in-distribution risk, right? Because if such a relationship exists, it has a number of important, number of important implications. For example, if such a relationship exists, then you know that your method, if it's going to perform better on in-distribution data, is also going to perform better on out-of-distribution data. So this really does not hold universally. So there are a lot of examples where it actually doesn't hold. So here's one example where it actually holds. So let's say we have a covariate shift. A covariate shift is the following. Let's say data comes from a Gaussian distribution with some covariance matrix P, and then the data is somewhat labeled through some labeling function. It doesn't matter so much which labeling function. So this could be a classification problem, or this could be a regression problem, right? So for different labeling functions, we get either a classification problem or a prediction problem and different kinds of problems. So if we have such a covariate shift and we look at regularized empirical risk minimization based on data from distribution P. So here the setup is these examples, xi and yi, they are drawn from distribution P. And then we solve this regularized empirical risk minimization problem, and depending on how much training data we choose and depending on how we regularize, we get different estimators. So this is really like a set of estimators. For different n, for different lambda, we get different estimators. And it turns out in the high-dimensional setup, you can show that the risks observed under those, like as a function of lambda and n, they obey such a monotonic risk relationship. And the particular function, so how the monotonic function looks like, that depends on the particular distribution shift. So it depends on these matrices, and it depends on the labeling functions, and it depends on the loss that you are choosing. But the point is, for such a setup, you really have such a monotonic risk relationship. Okay, so now another takeaway from this experiment on MRI was that the performance, no matter for which method, for L1 minimization and so on, for the neural networks, it drops significantly, right? And significantly means not just by a tiny amount, something that you can't see. If you look at the images, it just performs significantly worse than a distribution shift. So it's like a really important problem in practice. So then what we would like to do is we would like to improve the performance of those methods. And improving the performance of those methods really means moving them upwards here. I'm saying moving them upwards because we kind of know how to move them sidewards, right? Because that's what we have really been working on for years, right? Making them better and better. We can kind of walk on this line, but what we want to do is we want to improve the out-of-distribution performance. So now let's go back to Ludwig's paper. So it turns out that for classification, this is extremely hard. So for classification problems, natural distribution shifts are somewhat an open research problem, and I think this plot illustrates it really well, because what you see in this plot is there are different kind of points, and if you look at the brown points are models that are trained based on some robustness interventions. So essentially, there's a person writing a paper saying, you know, here's a robustness intervention, performs really well on some toy setup, maybe a covariate shift. But now if we apply this to real-world data, it doesn't really work, right? So that's the takeaway. The only thing that seems to work here is that if we train on more data. So there are some of these, so the green ones, those are all models that are trained on more data. What we can see here, there are some cases where if we train on more data, we get better performance. And training on more data in this case means not just more of the same, it means somewhat more diverse data. You know, it's difficult to measure, but that's effectively what it is. So now if we look at this plot from classification and just on the vast amount of literature that, or vast amount of things that people have attempted, it's kind of, you would think, oh, this is a really hard problem, there's not much hope. But it turns out that for image reconstruction problems, this, you know, adapting to distribution shifts problem is much easier than for classification. So there's, you know, there's a relatively simple solution. And I want to illustrate why it's a much simpler problem for image reconstruction problems, just to drive home this point. So let's say we want to improve the performance for L1 minimization. So we don't really want to improve the performance for L1 minimization, because even if we improve the performance for L1 minimization, neural networks are still better, right? So we wouldn't care, but just to make the point that the problem is really well posed. So for L1 minimization, we really have only one parameter to choose. So if we choose this parameter right, we get much better performance. So how can we choose this parameter? Well, we can just take our data and split it into data that we actually train on and into a validation set. And then we can solve our L1 regularized minimization problem, and we can do this for different lambda parameters, and then we can just choose the best lambda parameter. And by doing this, we pretty much perfectly adapt to the distribution. So this works really well because for L1 minimization, we only have one parameter to choose, right? And we have quite a bit of data if we have like undersampled data from a whole image. So the same thing obviously won't work for a neural network, because for a neural network we have 50 million parameters, so then we would somewhat overfit to the data, right? Because we can just fit it perfectly. But it, so you know, for L1 minimization, we can essentially take those points, move them up here, but then we are still not going to be better than the neural networks. So what we actually want to do is we want to move the neural networks up there. So what we can do for the neural networks is conceptually something very similar, and it's called a test time training. So the idea is to introduce like a self-supervised loss. And so this is a training stage. So the training stage, we train with respect to the supervised loss and with respect to a self-supervised loss. And the self-supervised loss only depends on our measurement. So it doesn't depend on the ground truth data. So we train our model, but then at inference, we're not just using our model, we are performing first test time training, and test time training means we are updating the parameters of the model by minimizing the self-supervised loss. So if we do that too much, we're going to overfit, but if we just do it a little bit, we are hitting a point that performs really well under distribution shifts. And then we reconstruct just by performing a forward pass through our model. So let's see how this works. So let's look at the anatomy shift. So anatomy shift is as follows. If we train on distribution P, that means if we train on the brains and then we test on the knees, that's the performance we get. So if we actually were to train on the knees and test on the knees, we get significantly better performance, right? So that's the performance that the model can give us if we train on the right data. And this gap, that is the performance gap. So that's by how much we can potentially improve for this particular model, right? It's model dependent also. So now if we do the following, if we train on Q and test on Q and do test time training, then we perform like a tiny bit better than this one here. The reason why we perform a tiny bit better is also really intuitive, because what we do here is we are doing test time training for every single example. So we are adapting really well to every single example. So that's why we're performing even a little bit better, but really just a tiny bit better than if we train on that data, right? Because here we are using the same parameters for each example, and here we adapt to each example, so we get slightly better performance. And here's what we get if we train on the distribution P and test on Q and do test time training, then we perform a little bit worse than that. And so this is what we call the performance gap after the test time training. There's still a performance gap, right? But it's just like very minimal after this test time training. And this approach of test time training works really well. So if we look at different, distribution shifts, then, I mean, it depends on the distribution shift, right? Doesn't perform universally well. But for example, if we have an anatomy shift, so for example, we train on knee, test on brain, then it closes this gap by 99%. If we have a data set shift from FastMI to Stanford, closes it by 87%. And if we have a modality shift, then by 96%. And, a saturation shift, 97%. So it performs really well for these common distribution shifts that we encounter in MRI. All right, so the conclusions are as follows. So there are marginal in-distribution gains from scaling beyond a few thousand examples. But there are significant gains that can be expected in practice from building distributionally robust models. So there are really two ways how you can build distributionally robust models. So either you can adapt at test time. That's expensive, right? Because you always have to update your model parameters. What the best option actually is to train on more diverse data. So if you're able to collect a data set that is very diverse, then this also gives you a model that is relatively distributionally robust, right? And I also want to argue that algorithms and better deep learning models have a huge potential to further improve performance for practical imaging problems, right? We saw at the beginning that if we just look at something very narrow, like for example, accelerated MRI, there's very little room for improvement. But if we go a little bit beyond that, then there's a lot of room for improvement. So one example is, let's look at cardiac MRI. So this is my heart, for example. You see it's a really poor reconstruction of my heart in a way, right? Because it's moving while we're reconstructing. But this is actually based on several gigabytes of data. So there's a lot of room to improve the performance for these kind of real-world imaging problems. All right, so here are the references. Those are the 4 papers I talked about. And yeah, with that, I would like to thank you very much for your attention.
We have time for questions.
Okay, hello. Thank you for the nice talk. So my question is regarding the test time training. So you mentioned that once we apply the test time training during inference, the distribution gain, the gap between the gains is decreased. So, and it is used using a self-supervised objective, right? So during this self-supervised training, so my question is, what part of the model is being trained or updated? Is it the full model or some particular portion of it? Thank you.
It's a good question. So in our case, the whole model is updated, actually. There are variants of this idea where only part of the model is updated. So for example, in classification, there are versions of this approach where only part of the model is updated. And for example, you could take a UNet and you could only update the encoder or the decoder, things like that. So we played around with this a little bit. In our case, it performs best if we update the whole model, actually. Yeah. But for example, there's like a paper, I think it's called gain tuning, where they have a model for denoising, and they want to adapt to different signal-to-noise ratios, and then they update the parameters of batch normalization. Then you just have much fewer parameters. This also works well.
Hi, thank you for the talk. So the self-consistency loss that was added, that stems from the observation that the reason the models earlier failed to distributional shift is because when you do the measurement of the reconstructed images, they were not close to the actual observed measurement.
That's a good question. So, in a way, so when you have you have certain frequencies, right? And then that's your measurement. You pass that through your network, then you're not actually reconstructing those frequencies perfectly, right? So, and if you have a distribution shift, typically you reconstruct them even worse than usually. And that's kind of where we started off in a way.
So it seems like there were two kinds of distributional shifts that you showed. One was when the types of scanner had different configuration of the same knee MRIs, and the other was like knee MRIs versus brain MRIs. So how does the self-consistency loss addition help with the brain distribution shift?
It's hard to say why it works. So we didn't, so we found examples of distribution shifts and test time training where you perfectly adapt to your model, right? But we, like this kind of toy models, they don't correspond to what we observe, right? Because in our case, it's also really hard to model, right? Because what distinguishes knees from brains, in a way, I mean, brains are just more smooth, right? And they're sometimes more dark and so on, depending on the contrast, right? It's really hard to say why it works, to be honest. Again, I mean, probably works on some toy models, but the toy models don't really model these distribution shifts. So I'm not sure what to take from this. I mean, in a way, it's also, we really tried a lot of ways to adapt to these distribution shifts, and this just worked really well, right? There are two things that probably play a role. One is that the loss is still a good one, right? Because you want to do well on you want to do at least well on the frequencies that you know. So it gives you some signal on where to go. The second thing that probably plays a big role is that if you actually have a neural network, like a CNN, it's a really good image prior, right? So even if it's completely untrained and you're doing this, if you're not doing this too much, you get really good performance, right? So even if you don't train your model at all. So probably those two things play together.
Also, sorry for the last question. Do you have any idea on why this is much harder to do in classification tasks?
Yeah, the intuition is really I think the L1 minimization illustrates it nicely, right? Because for L1 minimization, you really have an example where it's really trivial how to adapt to a distribution shift. And the reason why it's trivial is because you really, let's say for classification, right? You have an image and you have a label, but you have no information about the label whatsoever, right? Under distribution shift. But in image reconstruction problems, in a way you can split your data so that you have something that resembles labels, right? So you can actually also see how well you're doing, right? So for example, what you can do is you can take a MRI image, undersampled, and then you can reconstruct, and you just have a small holdout set, and then you can predict very well how well you're actually doing. For classification, there's no way of doing that, right? You cannot have an image, and then there's no way how you can estimate how well you're actually predicting a class, right? There's just no information about that. Whereas for image reconstruction problems, you do have such information. That's the intuition why it's just, much easier. It's also a huge problem, distribution shifts, but just much more well posed in a way.
Thank you so much.
I was thinking about a few works that we have kind of related to this, which is we tend to think of supervised methods as being population adaptive, so they are adapted to a certain population of data. And then we have these patient adaptive methods like deep image prior or dictionary learning methods that can adapt to every single image that you're trying to reconstruct. And so we have works where we try to integrate population adaptive and patient adaptive models into unrolled networks. So it seems like that this seems related, that you're doing test time training, and then if you have the models where part of the network is trained to the data that you're imaging, and part is sort of already pre-trained population adaptive, that would address similar issues.
Similar issues, yeah, exactly. Yeah, good point. Yeah.
Any further questions?
Yes. Oh, I have a question. Hi, I have a question about the test time training for this one parameter family of L1 minimization. So in this case, how does it compare with not using the training data at all? Right, so for every image, you can split it and then just tune this regularization parameter with a cross-validation. So that should already give you something. So how does the test time training really works here? Do you use SGD? Do you initialize with already trained data on distribution P, or are there special tricks that you do? Like, so more generally, the question is about, like, is it really working better than no training at all, basically tuning this parameter with one image?
L1 minimization works, like if you adapt to out-of-distribution data, it looks actually very similar to what we saw in terms of gap before. So like for L1, like, so for example here, so in this case, so this is, everything is specific for neural network, right? So now if you take L1 minimization, everything just shifts down essentially, right? Instead of 0.85, you're gonna have 0.75 or something, right? But other than that, it's exactly the same. So, yeah, so you also have, like, so for example, for P and Q, the regularization parameter for L1 minimization is like quite different actually, right? So you get like a big jump from getting that right. And then you get a tiny jump for every single image getting the regularization parameter right? Because if you optimize that for every single image, you're also getting like a tiny performance improvement. So it looks, for L1 minimization, looks exactly the same, just shifted. Yeah. Yeah, but again, like, you know, just want to emphasize I don't think this test time training is kind of the last answer, because it's really expensive, right? Because what we really gained, like one thing that we gained by using deep networks for these image reconstruction problems relative to something like L1 minimization is that it's so much faster. And this really matters if you have, you know, for example, the whole volume that you want to reconstruct. Now, if you do test time training, you're as slow as optimization-based approaches again, right? So what you would really like to do is ideally train on something that is like on a data set that is very diverse and kind of avoid the test time training. Yeah.
Hello, thank you for the talk. My question is, so during inference, when you are given an out-of-distribution measurement, you apply the self-supervised loss to that by using the same A matrix that you use during training. But it's possible that the measurements that you're doing inference on is generated by a slightly different forward model. So I was wondering, like, could you give a comment of whether that would impact the performance of test time training?
So one example of, it also works, right? So for example, like all those methods actually use the forward model. So for example, if you have a unit, you're not, your input is you're first doing least squares by using your forward model, and then you get a very coarse reconstruction, then you map your coarse reconstruction, right? So all those neural network-based methods actually use the forward model, right? But now if you have, like, say, 4 times undersampled data, you really want to, like, the artifacts that you have, that your network is trained to remove, are just different or slightly different than if you have 2 times undersampled data, right? And that part you can kind of adapt to using the test time training.
Okay.
Yeah.
Okay.
But it's kind of a different story. Like, let's say your forward model, it could also be that you get your forward model wrong, right? Then you lose even more. Because here we are assuming we get the forward model right. Yeah. And you do get your forward model wrong in practical applications, actually. So for example, like, what's very common is that a patient moves. like even if you have a brain, right, and you're just being there and you think you're not moving, even through your just your blood flow, your brain goes up and down actually, right? Like, or if you swallow, it moves significantly, right? So you always have movement, and then your forward mod is actually not slightly wrong, right? That also has a big impact on performance. That's why I think like things like you know, developing deep learning methods that work really well for moving objects is not exactly clear how to do that, but it would be extremely impactful. But that's another real-world application where you can really expect significant gains. Yeah.
Okay, so if there are no further questions, let's thank Reinhard for his wonderful talk. And